All right. Let us get started. So today we are going to be discussing two different topics that kind of build on each other. So the first is retrieval augmented generation. And this is going to set up another like little module within the semester where we move from LLMs as just single turn, you put in a prompt and you get a response. And we're going to move more to using LLMs as controllers of different kinds of both text generation as well as tools that they can access and update kind of internal state and memory that is kept in natural language. As a whole, this kind of these like LLM controlled systems are nowadays called agents or agentic. This word has I think just got created last year to refer to LLM agents. All right, so I guess at a high level, we're going to go from LLMs to systems. And we can see that as we discuss in this class and the next one, that we're going to be able to tackle increasingly more complex systems increasingly more complex tasks by combining LLMs with external APIs and environments. So, so far, what we've seen is we get a prompt, right? Like, write me a story. We've put this into our LLM, and it generates some response Y, and then we do whatever we want with that Y, right? We can evaluate it using whatever benchmark we care about, or we can use it for our downstream tasks. Today, we're going to discuss at a high level a kind of different setup where we do still start with a prompt X, but this is fed into an LLM that has access to tools and some kind of state or memory. And the LLM is allowed to call itself many times with different inputs, different tools, update the state before finally producing a response Y. So we will kind of trace the evolution of these kinds of systems over the last couple of years. Obviously, they rely heavily on very strong instruction following capabilities, right? Nowadays, if I tell a model, this is the task I want you to solve, you have access to these APIs and these functions that you can call. It will learn how to use those functions, combine them, and use them to solve whatever task it is that you want. So we'll start with just slightly modifying this first part with some external information. And so the first thing we'll talk about here is called retrieval augmented generation, or RAG for short. So this term was invented by people who were, I think, working at Facebook and then later are now at Cohere. But it has grown to kind of be this high-level sub-area of LLM research that tries to deal with like huge data sets and how can you get an LLM to kind of do things on top of very large data. Clearly, data that's larger than what you can fit into your prompt. So let's make some, like, what do we have here? So first, we assume in general that we have a frozen LLM p theta. So let's say this is our model that has gone through pre-training, fine-tuning, and RL. So we have our final, like, best instruction following model that we could train. Okay. So now, in order to use retrieval augmented generation, what we need in addition to our LLM is a data store. So this is where all of the external information that we want the LLM to operate on lives. So for example, if you are a finance company, you might have a bunch of financial documents about various companies that are proprietary, right? The LLM may not have been trained on these documents, but you still want it to, perform some tasks using those documents. So how can you do that? So at a high level, we want to create a data store. We'll call it D. And this term data store, again, is referring to the collection of all of these different documents, to retrieve from. So our high-level goal here is, given a prompt X, retrieve the top K most relevant docs, and we can call these Z1, Z2, up till ZK, from the data store. And then once we've done that, we will generate a response Y from the LLM, P theta Y given X. That's what we normally generate. But here, we'll include as additional context these retrieved documents. So, if I was a financial company and I was like, what is, my bank's profit in this quarter or something, from a data set of, possibly hundreds of thousands or millions of documents, you might want to pull the one that's relevant to your bank that has that statistic, put it into the prompt of the LLM so that the model has access to this information. So that's the kind of high-level idea. It's very simple. Generally, we're not actually training this LLM to use these documents. We will just modify its prompt at test time. Although, you can improve the model's ability to handle these documents by doing some training, like putting some data like this into the instruction tuning data set when we're doing SFT. But we can talk about that a bit later. So, all right, let's look at a simple example here. So, I actually forgot to look up the answer to this question, but actually maybe that's a good way for me to use Wikipedia. So what date was ERIB open to the public? So if I have this question, maybe ChatGPT will know this answer without any prompting, but it is pretty specific, and ERIB is not a super famous building in the grand scheme of things. So maybe it has not memorized the exact date in which ERIB was open to the public. So I could retrieve the ERIB wiki article. I assume it has one. Or maybe get this information from the UMD website, UMD CS website, other sources. Perhaps all of these things are in my data store, right? I'm, in this case, limited to things that are in my data store. So anything that's not in there is not going to be included. Now I will concatenate these documents to my prompt. And generally you can do this by having some special tokens. So I could say like doc1, you know, whatever text is on Wikipedia. Well, sorry. Doc2, whatever text is on the UMD CS page. And so on for all of the top K documents. So I'm going to take the text of these retrieved documents. I'm just going to concatenate them to the prompt after the question, right? What date was Arib open to the public? Then I will feed the combined prompt plus all of these documents to the language model to generate Y, the answer. Does that make sense? Any questions about this process? Yes.
Well, won't that make like the prompt super long though? So wouldn't that cost a lot?
That is a great point. So generally in retrieval augmented generation, because you are making the prompt super long, it gives you an inference cost. The argument against that is, well, for many of the use cases of RAG, I may not be able to actually get the right answer without having these documents, right? So it's a matter of like, what task are you working on? If you have like small enough context that you can just shove all the documents into your prompt and do no retrieval, then maybe you want to do that. But yeah, generally these data stores are huge, and K is relatively small, like maybe 50 or 100 chunks. Yeah.
I'm wondering the parameters for the last step is it following a certain template or something?
You mean in this step?
The fruit X.
Oh. No, it's this last step works just like decoding from a normal language model. So just think about your prompt as modified to include text from the retrieved documents. But you're still producing one word at a time, conditioned on both the prompt and the retrieved documents. Yeah.
When the prompt is becoming so large, would it be able to do the right attention mechanism because it's so long?
Yeah, we'll talk. So the question is, again, related to the length of the prompt. Wouldn't that maybe degrade the model's ability to handle this? Like, what if there's other, more complex things too? What if two documents have conflicting information? All of these things have been studied. Generally, for RAG, like if you don't care about the inference cost, then more documents, the better. So even if you fill up your context with 1 million tokens from many different documents, as long as one of them has the correct answer, you're generally going to see higher performance then. Yeah.
So given a prompt, how do we know which random box we should?
We will get to that next. Yeah, so there's a function that chooses this top K documents dynamically based on the prompt. Yeah. Okay, so let's talk about that. How do we perform retrieval, right? This is like the most important question here, because we rely heavily on the documents that we retrieve in order to respond to this prompt. So a simple way to do this is just say, well, I don't know how to do this, so I will just issue an API call to Google search and give it the prompt and retrieve, like the top 10 search results, shove all of those into my prompt and generate. This is actually a really good general purpose solution, but this doesn't work if you have proprietary documents, right, that are not like on the public internet. So we will talk about, what do we want to do in the case where the information in our data store is not easily accessible and we have to build our own kind of retrieval setup. Okay, so at a high level, we want to measure the similarity between the prompt X and the documents Z. And remember here we have like a huge number of documents, right? Potentially hundreds of millions or billions of documents at the largest scale. So what are some ways that we know to measure? Let's say I have a prompt and a candidate document, and I want to know how similar is this prompt to this document. What are some ways we could do this? Exactly. So how do we do this? I want to highlight two approaches. So this one that you suggest is the most common that currently is implemented in RAG systems, where we have what's called a vector database that relies on a pre-trained encoder model. So remember, an encoder model has bidirectional attention, like unmasked attention, and we can use our encoder to get a single vector representation of whatever text was fed into it, right? We can take the final layer last hidden state, or we can take, the average of all the final layer hidden states. Whatever we do, we are able to get a single vector at the end for each input. So just to draw that out more clearly, because it's been a while since we talked about encoders, we put some candidate text into, and generally these are transformer encoders. At the end, we want to extract a single vector. So again, this could be final layer or average of final layer hidden states, or some other function like that. Okay, before I get into how we actually compute the similarity, I do want to quickly talk about the simpler way to measure similarity of two strings. So what is another way, without using any neural networks, that I could measure how similar one text is to another text? So I could do some sort of word matching, right? We just saw with the blue score, it allows me to compute how similar are two texts. I could do something like the blue score or like any sort of simple string matching algorithm in order to compare the similarity of two strings. So, the first method at a high level works by just doing string matching. The most common string matching function for retrieval is a method called BM25, which is essentially a more fancy phrase matching algorithm that, as you said, upweights some like important words and downweights frequent words when computing the matching score. And the advantages of this are it's cheap and is actually very effective on many tasks, especially when the two texts you're comparing are long, so you have a lot of potential keywords that can be matched. What are some cons of this approach? So I'm just measuring like how many n-grams are common between the prompt and the candidate.
If the words are similar, you wouldn't be able to.
Right. Not good at measuring, say, semantic similarity. So if I have a paraphrase or I have a different way of saying something, I'm not going to be able to model that. Another thing is that here unlike in the blue score case, I'm not trying to look for equivalent texts, right? I don't want to retrieve something that is identical to my prompt. I want to retrieve things that are relevant to my prompt. And so this kind of method makes the assumption that anything that is relevant to my prompt has some string or phrase overlap with the prompt, but that's not necessarily always the case, right? Especially with more complicated tasks. So the idea is a vector database using this like large pre-trained encoder. We go beyond string matching and maybe are able to capture more of these kind of relevance signals rather than just exact match. All right. So let's get back to our vector DB now. It's easy to think about how in the string matching case we compute similarity. We just measure like overlapping n-grams. But in the vector database case, it's a little more complicated. So we are going to embed the prompt x and embed each document z in the data store. So now our data store consists of millions or billions of embeddings, one for each document. And whenever we get a new prompt, we can embed that prompt using the same model. And now we have a prompt embedding and a ton of document embeddings. So if I have vectors for a prompt and vectors for a bunch of documents, how can I compute a similarity between those vectors? Yeah.
Cosine similarity?
Sure, I could do cosine similarity, or more generally, I could just take the dot product as we've seen. So in practice, we do compute the cosine similarity, but you know, if your data store is large enough, it becomes really hard to do the exact dot product for all of the you know, billions of vectors in the database. So we do use approximations to these exact dot products. But the specific thing that we want to do is perform what's called identify the k nearest neighbors of x. And these k nearest neighbors are the documents in this data store. So for example, I could take x.z1, z1 is a document, maybe that's 5, x.z2 could be -8, x.z3 might be 0, x.z4 might be 29. And so here, if I wanted to take the you know, top two nearest neighbors, that would be z1 and z4. So in general, I'm going to set this k to something like 50 or 100 and have a lot of relevant documents that I retrieve and then concatenate to my prompt. Yeah.
So how do we identify the nearest neighbors? Like what method is used?
So we're looking for the maximum inner product between the prompt embedding and all of these documents. I will mention that generally exact nearest neighbors is intractable just due to compute. Like if you have billions of vectors in your data store, it's going to be very slow to do this. And so we generally use approximate KNN. The library that's most popular for this is called FACE, and it, I believe, was released by Facebook before they changed their name to Meta. It's a very good library for huge scale dot product. So you can check it out if you're, ever working on this. So again, this is the dot product here. And another question you might be wondering is, these dot products are only meaningful if we have a very powerful encoder model, right? So if I train a BERT and then use it for this purpose, it might be pretty good, but it's, again, not specialized to the relevance in particular, right? If I just use BERT-derived embeddings for my documents in the data store and my prompt, and I take the dot product, I'll be measuring something more like similarity rather than relevance. So generally, this encoder is fine-tuned on retrieval data sets. So data sets of query context pairs. And there's many of these data sets available online. So a lot of them look like question answering data sets where you might have a question like, what year was ERIB open to the public? And you know that the correct answer is in the Wikipedia article for ERIB. So what you would do during training is train the dot product of the prompt, the question, and the ERIB Wikipedia article to be very high when you compute those embeddings with your encoder model. And train the dot product of that question with all other Wikipedia articles to be low. We're not going to talk more in detail about these contrastive loss functions, but they're generally very useful for retrieval. Okay, any questions about this whole setup? Okay, let me check on Tube. No questions there. Okay. So I made this really convoluted diagram of how RAG works. Looking at it now, I don't know if I want to draw it here, but maybe we can go for it. And if it's confusing, just ask questions. So this is how RAG with a vector DB works. So the first thing we need to do before we receive any prompts at all is construct our data store. So I'll call this first step here data store construction. So here we take our documents. So maybe I'll call this doc1, doc2, docn. And I'm going to put all of these into our encoder. And the result is going to be my vector DB. So this is the vector for doc1. This is the vector for doc2, doc3, doc4, blah, blah, blah. So this whole thing we'll call the vector DB, millions plus documents. So this data store can get very large, right? If you imagine that each embedding and state-of-the-art embedding models are usually like 1,000 or 2,000 dimensions per embedding. Now I'm going to, have potentially billions of these. The storage costs are huge, and generally we're not going to be able to keep this on our GPU, in our GPU memory. It's that big. So there are specialized libraries for handling this. You might have heard of some of these vector database startups. There's a wave of these kinds of vector DB companies a couple years ago that raised a lot of money and now are kind of irrelevant. But we'll talk about why that is now. But the engineering challenges of this, like maintaining and ensuring fast querying, things like that, really more in line with like databases research. Yeah.
What should be the dimensionality of each of those vectors?
Yeah, so these are generally like 1024 or 2048D vectors. And we'll look a little bit later at some leaderboards of embedding models that are used for retrieval and take a look at how they're trained. Yeah. Okay, so this is our data store construction. And then this database here interacts with the text generation. So normally we wouldn't have this data store, but here if we receive a new prompt, the first thing we're going to do is send that prompt to, oh, sorry, I should use a different color. I'm going to send that prompt to the retriever. So, how should I draw this? Okay, maybe I send this prompt to the encoder and get a vector out of it. And then I compute the similarity between this vector and all of the vectors in my database. So at the end of this process, I will be left with millions of similarity scores, and I want to extract the top K documents. So once I do that, here I have the text of these documents. So doc1, doc_k. These are going to go into my LLM along with the prompt and together be used to produce the response Y. So you can see that normally we would just have this line from the prompt to the LLM and then producing the response Y. But before we can do any of that, we first have to do this retrieval with here the KNN search. And once we find the K nearest neighbors, we are then going to concatenate them to the prompt and generate the response. All right, any questions about this?
For the vectors that you create, so the length is like 1024, but if the document is like so large, wouldn't you lose some information when you...
Yeah, that's a great question. So we'll talk about this in a little bit. I'm just going to go over the pros and cons of this setup. That is a important negative of this. So let's think about first, before we talk about bad things, like why is RAG good? So what are some reasons why you might want to use RAG over just vanilla generation from the prompt? Yeah, so specific facts or maybe domain knowledge, something like that, may not be memorized by our LLM during pre-training, right? So if the model has not memorized the exact date that Erib was open to the public, it's never going to be able to answer that question correctly, right? So the only way that it can answer that correctly without updating its parameters is to provide that information externally. So similarly, another like follow-up of that is fresh knowledge. So all of these models are pre-trained on data up till some date, right? But what happens if there's a new news event and I want the model to be able to reason about that, or there's a new like quarterly report or something and I want to have the model do stuff about that? RAG provides a way to inject a pre-trained model that's been trained on stale data with new data that has been written after the model was pre-trained. Does that make sense? Okay, what is another potential benefit of RAG that you can see? You can. Yeah, we can lump that in with the first one. If you have proprietary or personal data, you can allow your model to operate over that data through RAG. Yeah.
This kind of goes with the first one, but you wouldn't have to like retrain a model. Like you can just use like existing model.
Yeah.
Or RAG on top of it.
Yeah, exactly. Again, kind of goes with the first one and the second one. Like, you don't want to retrain your model every time there's a new like news article, right? You want the model to be able to be somewhat robust to things that happen after its training. That said, you probably don't want to go years without retraining your model, right? It'll just there's one popular example of a couple years ago where if there's like a change in the president or something, the model will have a very hard time updating these kind of prior beliefs that it has gained through pre-training. So if some like very famous position changes or something, it's hard to just overwrite that with retrieved documents. In general, this is a active area of research called knowledge conflicts. So if you give the LLM some text that conflicts with the information it's acquired during pre-training, how does it behave? So there's several cool examples of this, and you can actually try and unlearn certain facts by tuning your language model to forget them and inject other facts into the model. We're not going to talk about any of that this semester, but if you look up model unlearning and knowledge editing, you can find papers on these topics. You have a question?
Like you could also like produce hallucinations. This is sort of
Yeah, no. This is I think we can say reduce hallucinations, which does go with number one, but also this allows us to do attribution, where now if I generate some response using these 10 documents, I can encourage my model to cite from those documents, right? I can encourage it to copy text from the documents, and then I can attribute the text that it's produced to specific human-written documents from my collection. So this concept of attribution is extremely important. If you have used any of the like kind of search augmented LLMs, things like Perplexity or any of these search engines, you'll note that whatever it generates, it always gives you links to websites that contain information related to the claims that it's making. Essentially, this allows you to connect generated text to source documents. However, unless you are doing verbatim copying from those documents, there are always problems with reliability. So this attribution is not always reliable. Oftentimes an LLM can misinterpret the retrieved docs, or even ignore the documents. That especially happens in cases of knowledge conflict. That's a good segue into the bad things about RAG. So one of the probably the most important failure mode of RAG is that retrieval is just really hard. Is really hard. So it's easy in certain cases, right? Like in this ERIB example, if I have any documents in my data store that mention the ERIB and UMD, it's probably relevant to answering this question. But for more complex kinds of queries, if I say, write an essay about the history of transformers in NLP or something, it's a much more complex task, and the retrieval process may not give you all of the documents that you would need to write a coherent essay. The other thing is that poor quality retrieval, so if, let's say I retrieve 50 documents and none of them is relevant, this often leads to worse performance than no retrieval. And this phenomenon has been observed numerous times for many different tasks where they have like vanilla LLM generation and then LLM that has access to like this huge knowledge source, maybe Wikipedia or some other search. And whatever they do on the RAG side, they're unable to beat the performance of just generating from the model with no retrieval. So it's a very challenging topic because we don't actually know what the model has memorized in its parameters, right? And so if you feed the model documents that are irrelevant or inconsistent, those may overwrite the model's correct knowledge that it's actually encoded within its parameters. So I want to make this distinction here between, because you'll see these terms a lot, parametric knowledge. This refers to knowledge encoded in the model's parameters. So like things that the model has memorized during the pre-training or post-training process. And this is in contrast with non-parametric knowledge, which is generally in the form of external documents or other context. And so the model may not have memorized this, may or may not have memorized this information that is in the data store. The real challenge in RAG is that we don't know what is in the model's parametric knowledge, and so we don't, as a result, know when the model needs to retrieve, as opposed to when it can rely on the knowledge in its parameters. So that's kind of the big tension here. Yeah.
Yeah, the retrieval is done before, so we have no idea what the knowledge of the model is, right?
The question is, well, we do retrieval before we do the generation, so we don't really know what, but even if we did retrieval while the model was generating, or we did it multiple times, we still wouldn't be able to tell what the model knows, right? We have no way of looking at, if we look at a trillion parameters, we have no way to interpret, oh, this is where this fact is, yeah.
What if we unlearn the model for the things that we want to do RAG on, and then
Did you say unlearn the model?
yeah, as you mentioned, and then do the RAG? Would that like make it better?
So the model unlearning process is also not something that's reliable. So people have found that in unlearning, you generally have like a fact, and you want the model to forget this fact. But you can have the model forget some forms of stating that fact, but oftentimes like paraphrases of it are still remembered by the model. So it's very hard to localize to like these neurons, or they are solely responsible for this fact and nothing else. That just doesn't happen in these models, yeah. Okay, great. So another thing that you had brought up previously is this idea of squeezing all of the information about a document into a single vector. So information loss when embedding the documents. This is generally handled by chunking. So if you have a very long document, you can chunk it into multiple smaller pieces, embed each piece. But chunking loses context, right? So if I have one chunk and I embed it independently of all of the other chunks, I may not know what is actually happening in that chunk taken completely out of context. So yeah, like overall, RAG it's very brittle. It has a lot of limitations, and as models are, getting better and better, scaled up with more pre-training data, like Gemini 3, apparently they scaled up, another like order of magnitude pre-training, and so it's less clear where exactly you need to use retrieval. Yeah. Yeah, I can put that down too. Increase inference cost as K increases, also as the chunk size maybe increases. So yeah, you're going to pay for any added performance with slower inference. Okay, so that is, oh yeah, go ahead.
Sorry, so when considering a model that has access to Google and like we provide the documents, how much would it be different if the document is also available online? Like would the model with RAG perform better than a model just like being able to access to Google?
Yeah, I mean, the thing is that a model with access to Google, you need to pay Google to use it, right? So you have to pay the API cost, whereas if you have your own proprietary data store, as long as you can run it on your own machines, you don't have to pay for that. But the downside is, and like I think this makes sense increasingly now for proprietary data, but less so for anything else. If like Google can index it and reach it, then you're better off if you care only about performance for doing this through search. And we'll see a little later and also in the next class that search has gotten a lot more powerful recently in terms of these language model agents that can actually do things like navigate the browser and click on things and zoom in. So there's a lot more you can get than just like text lookup now. Yeah. 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 So I think when you're using Google search, you don't actually do any ranking either. You just assume that the order in which the search results are, like, the top 10, top 20 search results, Google has already ranked them for you, right, with a very powerful ranking algorithm. So yeah, there's a whole field of information retrieval where they study things like query rewriting, where you might generate many forms of your prompt and issue all of them to search engine, and then kind of get the results and aggregate them somehow. But in general, yeah, you can just send your prompt straight as is to Google and get some search results, and probably they'll be pretty relevant.
How does the LLM behave if it receives the conflicting information?
Yeah, there's a lot of work studying this. Like what happens if one document has like one date and another document has another date for when Erib opened.
Between documents, but from what it has memorized through pre-training.
Oh yeah, that also happens all the time, and there's no definitive answer to your question. Sometimes it might ignore the document and go with what's in its parameters. Other times it might override what's in its parameters and go with what's in the document. It's not clear in what circumstances it does one or the other. It probably depends on how strongly the model has memorized that particular information, but also how it's presented in the retrieved documents. But yeah.
Is there any schema which has been developed to tackle this sort of issue?
Not that I know of. I don't think anything is very reliable for this. All right, so yes. Chunk size refers to if you have a long document, you have to break it up into smaller pieces in order to feed it into the embedding model, right? Because the embedding model has some maximum length. So if you increase the chunk size and you have, like 100 documents that you retrieve, each of which has 5,000 tokens, right? You're going to be using a lot more tokens than if those chunks are much smaller. So both the K and the chunk size determine the total context length. Yeah, K is the number of documents, sorry, retrieved. And the chunk size is sorry, I should say not docs, but the number of chunks retrieved. And then the chunk size, of course, is just multiplied with that to figure out the total token usage of the retrieval. All right, so now let's move from retrieval to more general tool use. So this concept of tool use kind of emerged a year or two after RAG was developed, and it kind of generalizes this notion of an LLM interacting with the environment somehow. So you can view retrieval as an example of a tool that the LLM can use. But in the RAG setup, at least this vanilla RAG setup, it's very simplified, right? So in RAG, retrieval happens prior to response generation. And it only happens one time, right? So you receive the prompt, you perform the retrieval, and then you concatenate all those documents and do your generation. So the LLM is not really acting as a controller of when to retrieve, right? It is part of a pipeline where retrieval happens and then generation happens. But we can make this a little more, give the LLM a little more control over when it chooses to activate these tools that you can give it access to. So what if the model could call different tools during the generation process? So now we're getting a little closer to the agent-based systems that we see today. So here, instead of just doing your tool call, like retrieval at the beginning, here we're going to let the model decide when it needs to use a tool. So for this, maybe I'll switch over to the browser here, and I wanted to show you this paper. So this was probably the first paper that came out that showed that you can take a pre-trained, fine-tuned RLHF language model and further fine-tune it so that it can call different types of tools during the generation process. So here, you can just, if we read this caption, the model autonomously decides to call different APIs, a QA system, a calculator, machine translation system, and a Wikipedia search engine to obtain information useful to complete a piece of text. So here they only show the response, but these tokens are all just generated by the LLM in response to some prompt. Now you see there's this kind of special tool call that has been issued. So what happens is the model produces a special token that indicates that it has started a tool call. Then it produces the name of the tool that it's going to call. That tool may have some arguments, right? So here it's calling some QA system that has been built with this question. And when it has finished generating the arguments that go into the tool, at runtime, before the model generates another token, the tool is executed and the result is then put into here. So we replace the tool call with the actual output from calling the tool. So in this case, Massachusetts Medical Society. And then once the model is finished, it produces some end tool call token and then continues generating normal text. So here you can see out of 1,400 participants, 400 parentheses or, and now the model wants to produce the percentage that 400 out of 1,400. So normally it would just generate the tokens of the answer, but if the LLM doesn't know how to do math properly, it might mess that up, right? So instead here, the model calls a special tool, which is just a simple calculator. So we see calculator 400 over 1,400. Now, as soon as the model has generated the tool function and the arguments, the tool call is executed. So we're not waiting until everything has been generated before one after another executing all of these functions. It's dynamically, as the model is generating token by token, you have like a parser that's running over the response so far. And once you find like a fully formed valid tool call, you execute it and then replace the tool call with the result and then continue generation. Does that high-level process make sense? Yes. Yes, yeah. So there are some special tokens that indicate when the tool call is actually beginning and ending. Yeah. Yeah. Yeah, so basically this right here is the tool plus the argument, right? And so you have running in the background some kind of parser that implements all of these tools. So you might have like some calculator API or program that you can put arbitrary mathematical expressions into, or you might have like a simple translation API, right, that does this kind of word level translation that you can quickly run and then plug into your response. Here, this is an example of RAG, kind of. It's a Wikipedia search, but unlike the RAG that we discussed, this is dynamic. So it only does the search when it feels like it needs to get more information about some topic. Yeah. Yeah. That's a great question. So this is, these are showing test time executions. But for training time, you are training the model to produce the tool and the argument of the tool. And then during training, you also show the output while running this. So what is actually happening here is, and we are not going to go through the exact training method in this paper, but essentially they take a pre-trained off-the-shelf language model and they put into the prompt, you have access to these tools, you can use them, and they run that on a bunch of prompts. And obviously it's not very good at using certain tools all the time. What they do is they run it over specific prompts where it would benefit if it used the tool properly. And they take all the instances for which the ground truth output of the prompt had a lower perplexity when the model used a tool as opposed to when it did not use a tool. So they basically gather a bunch of examples where the model successfully used a tool to produce a better response, and then they fine-tune their model on those responses. So the model gets better at using tools, and then it can kind of repeat this process. This is not the only way that you can improve a model's tool use abilities, but it is the first way that was proposed. Okay, so tool calling, kind of like a generalization of RAG to multiple different APIs and functions, as well as kind of dynamic calling of the tools during the generation process instead of before the generation process. All right, yes?
Will the answer of the tool be part of the, like it would be added, like as in the Z's that we added for like the Z's that we added in RAG, or just they be used as the next token that it
Yeah, they will be used as a next token. So here we're not just concatenating things to the prompt. We're doing a kind of token by token generation. Yeah, so here at test time, we'll actually be modifying the output to once the tool call has completed and we've received a response from the tool, we'll get rid of the actual tool call and just keep the output. But that's kind of a post-processing step that's done. All right, so in the last couple minutes here, I will introduce the most complex type of system that we'll be talking about in this class, which is the LLM agent. And we can discuss how that differs from the RAG and tool use stuff that we've seen to this point. Okay, so let me just write down here. I forgot to put the papers up for this week on the website, but I'll write down Toolformer and I'll update all of those on the website so you can check them out in more detail. So this is more for next class, but I'll give a quick overview here so you can think about this over the weekend. So far, we have seen how we can augment LLMs with retrieval and other tools. However, the whole process that we saw, even with the Toolformer, is still like we receive a prompt and the model generates a response. And the tool use is all happening like during the token by token generation of the final answer. So when we move from this kind of tool use setup to agents, we will allow the model to perform many different calls, not just one to complete the final generation. So the model might be able to produce several intermediate outputs that are not the final generation, pass any of those to other tools, process them further, access an environment and do things there, do like many different steps before finally deciding to produce the response. And so that is kind of the main difference. So at a high level, agents are LLMs with tools, but also with a dynamic control flow. So you don't know when you issue the prompt how many different calls the LLM will make, how many intermediate outputs it'll produce, what tools it will engage with, how the state will change. All of these kinds of things are unknown to you. There's also some notion of state or memory. So the LLM is actually taking actions in some environment that affects the state of the world. And so it's constantly issuing tool calls or API calls, querying the environment to see what the result of those were, and then deciding what to do next. All right, so we'll get way more into this in the next week, but I was just visiting Ohio State, where they have like 3 or 4 faculty who work exclusively on LLM agents, and they've published a lot of impactful papers on them. So I asked a couple of the professors, I was like, look, I'm teaching this class on agents tomorrow. What is an agent? Because there's so many definitions of this word, and also the adjective form agentic that people just kind of throw out in different papers and blogs and products, and they all have different kinds of interpretations of what it means. And actually, all of the professors I talked to had different answers as well. So the one I like the most, but is probably not accurate, but at least is easy to understand, is just LLMs in a for loop. So you have that gets the sense of like multiple LLM calls are being executed until either some number of steps or some end condition is reached. The other professor was like, no, I think there's some element of this. The LLM decides how those calls should look like, and that it's different based on the prompt. So there's this like dynamic control flow thing where the model is also acting as a kind of controller and planner on what kind of actions it should take. So that also seems important. Some people think RAG is an agent, so that's probably like the most inclusive definition, where any sort of interaction with between the LLM and some external thing that is not part of the LLM, you could consider an agent. But I think probably like what we can highlight is this kind of dynamic control that the LLM has over its actions, and this idea that there are multiple calls to the LLM with different prompts and tools being issued, and that the control of that is entirely up to the LLM. So it's kind of like LLMs and tools in some sort of looping construction. Okay, any questions about stuff that we've discussed so far? Okay, so where we're going is in the next week, we'll talk a lot more about agents. We will then come back to all the stuff we discussed with benchmarks, because you can imagine if benchmarking LLMs is hard, benchmarking agents is extremely hard. So some of the benchmarks that we see for agents are actually ridiculous. Like we have now AI scientists, right? And the way that those are evaluated is they come up with an idea for a research paper, they execute a bunch of experiments, they write up the paper, they submit the paper to a conference, and sometimes the papers get accepted, and that's like a win for an AI scientist, right? So this is like, a very time-consuming evaluation, possibly an unethical, or well, not possibly, it's just straight up unethical, wasting time of reviewers who are reading these, AI papers. But yeah, like the evaluation challenges when you have this very complicated pipeline are much larger than just a single call to an LLM. So yeah, we will discuss that more next week.